We're finally going to get into some math. We have taxed your patience long enough talking about thoughts and feelings and philosophies. Let's roll up our sleeves and do some real numbers work here. All of the math that we're going to really be going over, though, is focused not in proving the symmetrical components method from bottom to top or anything like that. It's going to be surrounding what you're most likely going to see on a Power PE test. And so what we're going to be working over is something like if you are given symmetrical formulas, what you would do to find one of the terms. So in this first example, what we're going to do is we are going to move from, if you are given a unbalanced phasor, the math you need to do to derive one of the component phasors. So we're moving from unbalanced to component phasor. And in order to do that, you employ one of the three equations we've written up here. So for these formulas, let's identify some of the variables we've shown here. So all of the v's on the right side of the equals sign represent the unbalanced phasor. So we're talking about a voltage phasor, and we are saying voltage phasor A, voltage phasor B, voltage phasor C. All of those are the right side of the equals sign. On the left side, we're talking about the component phasors there. So up there on our first one, we have VA0, which means it's the zero sequence voltage phasor component. The second one is VA positive or VA plus. That is the positive sequence voltage component phasor. And then the third one is obviously the negative sequence voltage component phasor. So just to be clear, that's what we're working with. So once again, we are working from supplied information with the unbalanced phasor, looking to derive the component phasor. The other variable we see that sticks out is the bottom two of these formulas have A. And the A is associated with the added complexity of the two sequences, positive and negative. And it deals with the complexity associated with the phase shift for the positive sequence and the phase shift for the negative sequence. Obviously, in the zero sequence, there is no phase shift, so that A variable is absent in that particular formula. These three formulas up here can be represented in matrix math by this construct here below. So both are essentially the same. One's spelled out in a non-matrix form and the other one is in matrix form. Now it's important to know with these formulas, what it's doing really is it's breaking down three phasors, three unbalanced phasors, and it's pulling them out into a total of 9 phasors in all, 3 phasors each. Just like we talked about, one of the controlling factors of symmetrical components is that the component phasors that make up the balanced phasor total are 3 in number. Now it's interesting to notice that these 3 formulas at the top can be represented in these connective lines that you see here. So in the A positive sequence, that connection from the unbalanced phasor to the component phasor can be shown in that formula. The negative sequence can be shown and the zero sequence can be shown. So they all match up. Now our variables that we're using in this instance are all for the A phasor. Now all we have to do is switch them over to the B phasor and we get that second cluster of 3 and the C phasor, the third cluster of 3. Now let's look at the formulas that work in the opposite direction. And what I mean by that is if you were supplied with one of the component phasors values, how to derive the unbalanced phasors values in the formulas. So we're going to leave the first set of formulas up so we can kind of compare and contrast as we work through. Now you can see the variables that we're identifying for this set of formulas are in a sense the opposite of what the 3 were above. And what I mean by that is the voltage variables on the right of the equals sign now represent the component variables, or the component phasors rather, and on the left of the equals sign are the unbalanced phasors. As before, when we showed the top 3 applied to the matrix on the top, these bottom 3 that we're working through now apply to the matrix on the bottom here. Now just to make sure that we're distinguishing this new set is before we were going from unbalanced to component phasor, and now we're going from these top component phasors and we are working towards the unbalanced phasor. Yet again, notice the use of the a variable in the formulas here. It functions in the same way as it did to the formulas above, as in dealing with the phasor angle shift for the positive and the negative sequences. And just as we're working in an opposite direction from where we start to where we work towards, we're going to sort of flip that tree diagram that we worked with the equations above to demonstrate how this applies to the flow of content from where we start to where we finish with these formulas. So this component phasor applies to here, while this component phasor applies there, and finally the negative sequence one applies here. And what this represents is we're using the component ones to recombine them back into the original unbalanced phasor. So we have really actually pretty simple mathematics, simple addition occurring with these formulas. It can be visualized as head-to-tail vector mathematics and so forth. Simple addition is occurring here in these other formulas. And as we saw before, they can apply to all sequences and all phasors. Have these formulas and these visuals in your notes when you go into the PE test. Now, it may seem like we've really spent a very cursory exposition into the math behind the symmetrical components analysis and methods, but really what we've given you is the real core that is going to most likely be expected of you in your knowledge base when taking the PE. But this content that you see on the screen here before you can be spun out in any number of different ways. So a PE question dealing with symmetrical components, especially on the math side of things, can use this information in different ways. It can supply you with various populating givens of the variables that we have demonstrated here, so that it can give you a component phasor, or it can give you one of the original unbalanced phasors, or any number of the ways. It can reference the matrices that we've shown below. So it's important that you not only just see this and have it copied down in your notes for the test time, but that you understand at the very least these fundamental concepts here of the symmetrical components. You can bet that some aspect of this is going to be tested in your Power PE exam. Now, the PE can ask you math-based questions like we've just discussed, but it can also ask you sort of theoretical, visual-based questions. And so, for example, these positive, negative, and zero sequence sorts of things, you could be asked, what sequence is this? And you should obviously have the understanding of the operations of symmetrical components method to be able to understand how to answer that question. So if you were given all three vectors with the same magnitude pointing in the same direction, you should know through this video series now what phase sequence or what sequence that is, and it's zero sequence vectors, etc. So be prepared not only for the mathematical side, but sort of for the visual, conceptual side of the symmetrical components analysis in your PE exam. So this mysterious and somewhat complicated method that has plagued a lot of electrical engineers while taking the PE test, now we've gone through really all of the core concepts. Let's take a step back and look at all the ground that we've covered, look at the formulas, make sure we have understood all of what we've supplied here, and realize that we've completed it. There's really not much more that you're going to need to know. So get this stuff learned, and we are done. Congratulations, symmetrical components. You got it in the bag.